So some of you lost the points on this quiz. And if you assume the first state at our beginning is 0, look at it. If that was 0 at the very beginning, and because this floating edge is going to sample this 0, right? So whenever the rising edge is trying to trigger the change at Q, it's not going to change anything because it was 0 already. And then this floating edge is going to sample this 1 here. And you can expect as this rising edge is going to trigger the change because it was 0. And after this floating edge, it already sampled a 1 to the middle stage, right? That's why it's going to trigger the change. And here, the floating edge is still before that floating edge of the data. So it's going to sample a 1. So that's why at the next rising edge, it's not going to change anything. It's still 1. It's going to keep that 1 here. And the floating edge here is going to sample a 0. And that's why this rising edge is going to toggle that Q, right? Okay. Sample a 1, trigger a 1. So it actually changes here. So I'm wrong at this point. It's not correct. So actually going to trigger a change because this one is going to sample a 1. It's going to trigger a change here. And then sample a 1 again. Okay. So it's not going to change as this rising edge. It's going to keep that 1. And sample a 0, so that's why as this rising edge is going to toggle this 1 and make it a 0. And sample a 0 here. So rising edge not going to change anything. Sample a 1, rising edge is going to trigger the change. Sample a 1, not going to change anything at the next rising edge. Sample a 0, it's going to toggle it. Sample a 1, it's going to toggle it. Sample a 1, not going to change anything. Sample a 0, toggle it. Sample a 0 here, right? So it's not going to change anything. And sample a 1, it's going to toggle it. Is that clear? Okay. So let's look at the calendar. We have one homework due on Wednesday, and there will be a quiz on Wednesday as well. On Friday, there's no class. And today at 10 p.m. is the lab 3 will be due. Lab 3 or lab 4? Lab 4. 4, yeah. Okay. And there will be a homework. You guys will be ready to do it after today's class. And there are a lot of simulations in there and in electrical VLSI. So if you have time, please do it sooner than later, so you can make it before next Wednesday. So it's due next Wednesday. It's not due next Monday because I know there's a long weekend. I hope you guys can have less homework in the long weekend. So that's why it's due Wednesday. All right. Any questions on anything? No? Homework? Quiz? All right. So we are going to work on high-speed flighters this time because one of the labs in the following weeks will be a flighter design, but it's, flighter is simple. We have learned it in digital logic, right? It's pretty fairly simple combinational logic. But if you are being asked to design a high-speed flighter, it has to be a AOI logic being designed in the complex CMOS circuits. So we have to revisit the structure of the flighter. And one more thing. So for just general combinational logic design. Combinational digital logic design. Should start from where? I mean, if the customer tell you that we need a circuit, digital circuit from this truth table, or from this input and output. So we want to start with the truth table, right? I just told you the answer. I'll start with the truth table. Remember the counter we talked about for the SAR ADC? If it's a 8-bit SAR ADC, we need 10 cycles. So we need 9 cycles to get the data done, to get the data converted. And so we need the 10th cycle to send it out. So we need a 10 count to 10 counter, right? But how do you design that? That's just one example before we get into the others, but this is just one example. So just relax, okay? Just don't think about that complicated. It just, if I need a combinational logic, it's very simple, just with all the logic gates. And all the other inputs should be zeros, should give you a 0 output. But only when it counts to 10, it gives you a 1 to trigger the flip-flops clock or giving a rising edge. How to do it? It's probably too many bits, right? So what if it's no, it's not too many. It's 8 bits RDC, but it's just only need to count to 10, right? So how many bits do you need for the counter? Three or four? 4. So you need 4 bits. For example, A3, A2, A1, A0, and here's the counter's output. Starting from this, that's how to design the digital circuit. Keep in mind, that's when we are getting started, right? So that's a requirement. That's what being asked from the customer. That's what we want to do to get it done, right? And that's where you want to start designing your digital system. So starting from those zeros, and then just lay out all the combinations of the inputs. And at some point, there will be a 10 here. It's 1, 0, 1, 0, that's a 10. And then keep going. Eventually, you have 1, 1, 1, 1. So totally 16 combinations. But only this one give you a 1, but all the other ones are zeros. Is that correct? So you are thinking about, hey, you're just counting to 10, and it's going to set the output. So it's been zeros until 10. So it's going to set. And then you want to invert this signal and reset the counter. So actually not going to count after 10. So all these like 1, 0, 1, 1, this just won't even happen, which is totally okay, but you still don't want to give any ones. Just in case there's some errors in the circuit, this kind of combination appears as an input and it's giving you a 1. You just don't want that to happen, right? Just all zeros with all the other inputs. So after we put all the numbers, inputs, outputs in the truth table, because there are no other possibilities for this digital system. These are all the inputs, these are all the outputs. And that's it, that's everything for the digital block. Okay, what's the next step? The purpose is to get a circuit, implement that goal. But we have to model it in here first, and then convert to a digital circuit. But now we have this truth table already. Can you directly find a digital circuit out from this truth table or not? By what? Yeah, so what's the next step though to get the gates? So in digital computer logic design in 241, the online class you took, after you get a truth table, what's the next step usually? If you have not too many bits, like 3 or 4 as a maximum probably, 2, 3. Is that the K map? So you can simplify it, right? And then get all the logic expressions for the output. But do we need a K map here? It's just one, you only have one here, right? You don't need to simplify anything. If you got one here, you got 3 of them, probably you want to put them in the table and can combine the neighboring ones and trying to simplify it first. But now we only have one. So you only need this. So can you find a logic expression out of it? And what is it? What is that logic expression? So y equals to what? And why this works for this truth table? It's an AND logic, and it has to be, since these are ones, so these both of A0 and A2 has to be zeros to make it 1 here, because it's an AND logic. Only when these two are zeros, when you invert it, you got 2 ones. So you got 4 ones, you got a 1 out of it. So this logic expression covers everything in this truth table. Okay? If you don't believe it, just plug in all the inputs to here, and it's going to give you the correct output. So that's how you get the logic expression of the truth table. And then you can find out the logic gates, right? It's pretty simple right now. So it's only like A3, A2, A1, A0. You just invert A2 and A0. And then add them together. So that's a computational logic you want to connect to your counter. You have a 4-bit counter. So that's the queues. These are the queues of the counters. All right. So what about the adder, the full adder? So we're trying to design a high-speed full adder. So starting from the very beginning, the logic expressions. So first, here's a symbol of the full adder, and there are 3 inputs and 2 outputs. S carry out, A, B carry in. So 3 inputs, 2 outputs. A, B, C, I, S, C0. So when you have 2 outputs, you have to do one by one, just one column by one column. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. So for this one, the summation is 0, carry out the 0, summation is 1, carry out the 1, 1, oh, 0, 0. And S is 0, carry out is 1, S is 1, carry out is 0, 0, 1, 0, 1, 1, 1. There's a question. How do you design a circuit from here? How that works? You have to do them separately. S is one circuit, CO is another circuit. For S, start with the K-map because you have multiple outputs or ones. So if you just eyeball it, probably cannot find out the simplified version. But you'll find out, even though you lay out the K-map, you can still not simplify it. But anyway, you just want to do it first. So for S, you have A, B, C, I, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, right? So what's next? Just fill in the numbers into the table, into the map. 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1. You just couldn't do anything. So you just wasted 1 minute in your life. You got thousands or millions of minutes, so that's fine. So what's the result, though? So S equals to, just write it down, right? So you have this one, it's A naught, B naught, Ci, or A naught, B, Ci naught. Okay? Or A, B naught, Ci naught, or A, B, Ci. Let's try to simplify this one if we can. Manually, not from the map. So the map is useless here, right? So we can combine these two and then these two together. So we're getting A naught, B naught, or AB, Ci, or A naught B, or AB naught, and Ci naught. So that's literally A XNOR B Ci, or A X or B Ci naught. And we know that XNOR is the inverse of XOR, right? So we can directly just do this. And you get another XOR logic. If you treat this part as a one entity, one black box. So it's another XOR logic. So it's going to be this XOR this, or it's this. It's just the two XOR gates to get S. So for S in this full adder, part of the circuit, so the top logic block to get your S is this. And so that's S, right? Now let's look at CI. Since we have to do it separately, there are two outputs, which means two outputs means you need two circuit blocks right, to serve these two different purposes. And the second logic block is for CO. See how that looks for CO. Still have to come back to the truth table. The first one appears here, and the input combination is A naught or 0, 1, 1. Let's just do 0, 1, 1, 0, 1, 1. And then this one here is 1, 0, 1, 1, 0, 1. And this is 1, 1, 0, 1, 1, 0. And the last one is 1, 1, 1 for this one, right? It's 1, 1, 1, the input. This looks better since we can at least simplify it. So how would you want to do it? Can you group 3 of them at once? No, just 2s or 4s, right? Yeah. Huh? Yeah. So 3 groups. So these are, so CO equals to, let's look at the first one. So A is toggle, so it's canceled. Only leave BCI here. And for these two, you have A and B is toggled, so it's ACI. And these two, you got A, CI is toggled, so it's AB. So this is actually A or B, CI or AB. And you can directly draw a combinational logic circuit from this logic expression. You have all the gates, all the signal lines. It's pretty simple. But we don't want to use that structure, the old-fashioned flatter structure. It's just too slow. So we want to use AOI logic. But we want to start from here, right? So you understand the logic or the logic expression for the flatter. So that's a 1-bit flatter. How can you form a 3-bit flatter? So keep in mind, you do have 3 inputs for this flatter, but it's not a 3-bit flatter. You understand the difference? Someone asks you, is this a 1-bit or 3-bit flatter? And why? It's a 1-bit flatter. Why it's not 3-bit flatter? A and B are 1-bit binary numbers. It's not like you have like B2, B0, B1, B1, B0 plus A2, A1, A0. And then you need a 3-bit flatter. But this guy is only like B plus A. Done. That's why even though you have 3 inputs, it's actually a 1-bit flatter. And if you want to make a 3-bit flatter out of it, you need 3 of them. So here's how you design the logic blocks. 1, 2, 3. Just adding from the right hand side. That's why this is the LSB. And the first carry in, because every flatter, they are just the same circuit, you're just reusing the same block. So everyone has a carry in. But when you're adding 2 numbers together, like B2, B1, B0 being added to A2, A1, A0. You're trying to add them bit by bit. There might be a carry out from this addition, so you can carry it out here. The thing is there's no carry in for these two bits. Is there a carry in? No. So the thing is you still need to short this one somewhere else, right? So we just label this one as C minus 1. That's a carry in for the first block. And that's A and B, A and B, A and B. So the carry out is being shorted to the carry in for the next stage. Same for this one. And we can label the carry here to be C0, C1, and that's C2. And these are the S, the summations. And that's A0, A1, A2, and that's B0, B1, B2. So this circuit is going to implement this addition for you. And that's the 3-bit full adder. And it's called a ripple carry adder. Or RCA. Because the subsequent stage has to wait for the carry out to be calculated first to get a correct answer for the next stage, right? So it's like the carry is rippled to all the stages. It's called RCA, ripple carry adder. It's kind of slow if you have all these doesn't matter what kind of adders you have, it's going to be slower compared to, there's another structure called carry look ahead adder. It's a little bit faster than this. But anyway, this is a very common design. It's fine to use it, okay? So what's the final result? How many bits are in the final result? No, how many bits? Final result. So 3 plus 3 bit plus 3 bit. Is that possible like you have 5 bits for the final result? It won't be 3 because if there's a carry out happens, then you have 4 bits for the output. For example, you got a 1, 1 here, right? 1 plus 1, you got a 1, 0. So it ends up with 4 bits. It's not, doesn't have to be, it's not necessary to be overflow. It's just a carry. So remember overflow, the concept is different compared to carry out. That's another story. It takes a lot of efforts to figure out that one. So in the spring semester, I assume you guys, all of you guys probably, I think, it will take CE433. Have you taken that class in the past? Not yet. So take that class and we'll have a FPGA project on that little, it's a 4-bit or 3-bit, I forgot. It's a FEN subtractor design to address that overflow and tooth complement issue on the hardware, so you understand the details about it. But now we're not talking about overflow because they are all positive numbers. There's no tooth complement by far. And there will be another subtractor we're going to talk about pretty soon. We'll take care of tooth complement. But now it's not tooth complement. It's totally positive numbers. So although you have this, and we are considering this number as what? 8. If it's a tooth complement, so what is this number? So first, what is tooth complement? It's good to have a review since we have to talk about it sooner or later. So what is tooth complement? Inverse first, add a 1 to get a negative number, right? So for instance, we have, so what is negative 6? You have a 4-bit computer system, so which means I have 4 4 bits, 4 slots, or 4 memory bits to hold the numbers, okay? Then what is -6 in this 4-bit computer system? So first, do I have enough bits to make this happen? Yes. So how can I tell? You can give examples, but is there a rule or something you can follow, a standard you can follow? Yeah, so if I have 4 spots here, so what is this one represent? It's always a negative number if I got a 1 here, right? So if I put a 1 here, then it's going to be -8. It's not 8. That's how you use 2's complement in a binary system. Just keep in mind, just memorize it. Like you want to ask why? Why is -a? We just define it to be -a. It's actually not -a. It's just a logic high on one of the memory bit, but nothing else. It's just a logic high. So I need to plus a positive 2 to make a -6. Okay, that's how I calculate it in an easier way. But by the definition, by the concept, you can still convert something back to convert something to this to make a -6. How to do that? So you have a 6. Oh, that's 6, right? You want to inverse every bit and plus 1. Oh, plus 1. Carry 1. Same result, right? That's how you use 2's complement. All right, a quick review on this. But here, there's no 2's complement. It's a positive number, all positive. How many bits do you have for the final result? And what are they? So there might be carries carry out from this addition and being used as a carry in for this addition, and the same for the carry out being used as a carry in and eventually get a carry out, and which I just labeled as C2. So whatever here will be the MSB. Can be 0, can be 1, doesn't matter. And all the S as these 3 bits will be these ones. So C2 as 2 as 1 as 0 will be the final result. And that's the ripple carry adder. Then let's see. Can you so what's the other way you can add a 3? Can you use 2 FAs to add a 3 1-bit numbers? Is that necessary to talk about that? I mean, just let you know. So if I have an FA here and FA here, AB, I got another number to be added to A and B. If I ground the CI here, right, but still have A and B, and then I put a C here, and so the summation from these two, and I ground the CI here as well. So S and CO is still the final result. Is that correct? So the FA has 3 inputs. If I'm not connecting anything to CI, so S equals to A or B. They're asking what is CO being used here? Do we need a CO?
We don't need a carry at the end.
Uh-huh.
In your last example, the carry was at the very end. That's the only one you were concerned about.
Yeah, so what about the carry out here from this station? Is it being taken care of?
Yeah.
But that's a sum.
From that end to the right end.
Mm-hmm.
Isn't it carrying carry out over?
So if you have a 1, 1 here, right? And eventually the result here will be 0. So it seems like this is not correct because I want to do this probably, right? Okay. Subtractor. Or when you are doing a subtraction, it's actually adding a negative number. Whenever you get a negative number involved, you want to use 2's complement. But the adder doesn't know it. We have to tell the adder what to do. The adder is able to add binary numbers and just do the operation. The thing is, it's a negative number, it's still a binary number. You don't have to do some special things for the MSB1 here, right? I know it's a sign, but it's also a negative number. But when you're doing addition, you should directly add it to something, right? If you have another one, then what's going to happen? 0, 0, 0, 1, 0. So what's happening? So this is negative A, and you are expecting negative 16, and it is negative 16. Okay. So if we want to use the similar structure to implement a subtraction, how do we do that? Yeah, you want to flip it. So here's B2, B1, B0, A2, A1, A0, C0, C1, C2, S2, S1, S0, and that's the final result. But when we are having a A2, A1, A0 minus B2, B, it has to be a plus negative, right? Because the adder can only do addition but not subtraction. So I have to convert B2, B1, B0 into its negative format. I have to negate it. How to do it? 2's complement. So we need to flip every bit in the B's and add a 1 to it. That's defined by the algorithm, right? That's how you do 2's complement. So yeah, if I have all these XOR gates, right, there are XOR gates here. So if I have B XOR with 1, then what's the result? So think about it. B1 or B1 not. So it's going to be B not or 0, which is B not. Is that correct? So if I XOR this bit with a 1, I'm actually inverting it. So I can connect this pin, have a little switch to short it to 1. Then at the same time, I feed this one to C minus 1 as the original carry in from the LSB. So I'm inverting it and also adding a 1 to it at the same time. Is that correct? If I switch it to 0, then you have B XOR 0, B not 0, or B 0 not, which is 0 or B. If you XOR B with a 0, then it's still that same, still B. It's not changing anything. So if I just switch it to 0, then it's adding a 0 to the carry. It's not adding anything. It's not changing B as well. So the B will be passed through the XOR gate to here and giving you the original B's. So doing addition instead of subtraction, right? So you can use a little control bit to do either addition or subtraction using the same flatter. Is there another way to do it, to implement the same function? I'm going to introduce mux. For you guys to remember mux, what is a mux? Multiplexer. Reason I want to use a mux is it's a 4-transistor circuit. It saves you a lot of space. But let's look at the mux first. So what is a mux? How do you design a mux? So the logic block looks like this, right? So you have A0, A1, have 2 signal lines, and you got a control bit to select which one you want to send to Y. It's a 2-to-1 mux. And I already described the logic or the function of this block. So that's a requirement from the customer. They just tell you, I want to do this. I want to have 2 inputs and 1 selector. And so I can send whichever to Y, depends on the state of this selector bit. And you are being asked to design the digital circuit out of it. What's the starting point? What's the starting point? So this has been a weakness of our students. From the competency exam we did last time, we found out students are not very good at converting a specific problem being described in English, just in the language, and convert it into and model it into a digital circuit. So what's the starting point? But before you draw the gates, how do you know which gates to draw and how to connect them? Truth table. Yeah, logic, truth table. So before you do the truth table, you want to find out what. So definitely draw a block first, right? And you want to figure out what are what. Yes. What are the inputs? And yes, is it as an input or output? Yeah, you have to select it. Have to give a high, give a low. That's from the user, right? The A or S, it's not S1, just S, A0, A1. You have 3 inputs, 1 output. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So when S is 0, you want to directly send A0 to what? So directly copy A0. What do you have for A0 for this for S? And when S is 1, you want to directly send A1 to Y, right? Do you have, how many outputs do you have? 1. How many K-map do you need to draw? 1. That's for Y, right? Where are the ones? So the first one is S. So for S, A0, A1 is 0, 1, 0, 0, 1, 0, and 0, 1, 1, 0, 1, 1. Here, 1, 0, 1, 1, 0, 1. Here, 1, 1, 1. Definitely, you can do this and this, which is okay. Yeah. Which one? This one?
Yep. What's that?
It's just one. Oh, the line? What do you mean?
Oh, I see. I was getting confused.
Oh, sorry. I just split the two parts because these are S are zeros. These are ones. Yeah. You can do this, but what's the problem? It's difficult to still memorize this homework assignment in logic. That's a static one hazard. Static one hazard. So we want to group these two to avoid the hazard, which is going to add one more term in here, right? So y equals to, so these two will be S naught, A0, or these two will be S, A1, or these two is A0, A1, so there are just too many gates. We don't want to use this version of the 2-to-1 mux. And there's a four transistor 2-to-1 mux. A simplified version looks like this. So that's a 4 transistor circuit. This is definitely not a full transistor circuit. How many transistors do you have over here? At least a 10, right? 10 to 15 or something. So Si is the inverse of S. And this is a transmission gate. And when you have a clock here, and you want to invert the clock here to pass A to B, So this box here is just just one PMOS on the top and one NMOS at the bottom, like this, right? And the reason we need two gates is because PMOS is good at passing ones and NMOS is good at passing zeros. It's better to have both of them instead of just the one. If you only have NMOS, you just turn it on, right? Just short this one to VDD and you want to pass A to B. It's not the best choice because it's not able to pass VDD, the whole VDD from here to here. The highest value you can pass through the NMOS pass gate. This is called PG, pass gate. This is called transmission gate, TG. So the highest voltage you can pass through the NMOS pass gate is what? So what's the highest voltage here can be passed to B if you turn it on using VDD at the gate? No, it cannot pass VDD to here. So the highest will be VDD minus VTHN. Because if you consider this as a source, VGS will be VDD minus this. And you end up with VTHN, which is the threshold voltage to turn it on, to keep it on, right? So that's the largest voltage you can pass through a pass gate. But the thing is, it's lower than VDD, so you are not actually passing VDD over to B. Okay, so we'll talk about the C diagrams and circuit design for the high-speed adder on Wednesday. All right.